Woo! Okay. People, let's start. Okay. We're nearing the end of the block, so we already see the midterm. Okay, people? The midterm is in the week of the 16th of October. Forgot the exact date, okay? Not far away. You might want to start practicing it. So I want to say a few words about the midterm. We will next week. It's going to be all about the midterm. I'm not giving you new material. If you still read the textbook, you might have noticed that we reached the last stages of the text. So next week we're going to do preparation. I'll say a few things about the midterm. First, a very nice lesson from the tutorial for the people who have been there. I tried to give you this on the board, but it was too messy, so I'm writing it here. We talked about the fact that the order matters both of the quantifiers and of the relationships, and the combination between quantifiers and relationships, okay? So if S is person 1, C is person 2, and I have 3 people, I can have, and 2 quantifiers, universal and existential, I'm going to have 4 possibilities of what can I say with that. I can say, everyone sees someone. For all X, there is a Y such that X sees Y, okay? You see this in this picture here. Every point you pick is going to see someone else. If you think about the arrow as seeing. You can keep the same ordering of the quantifiers and flip the ordering in the relationship. This gets you, everyone is seen by someone. For all X, there is a Y such that Y sees the original X you started with. So in this picture, it's not true that everyone sees someone because C doesn't see anyone, but everyone is indeed seen by someone. Okay? Now we can flip the orders of the quantifiers and we get sentence like 3. Someone sees everyone. There is an X such that for all Y, X sees Y. Who is this X in this picture? Who is the X that sees everyone? A, correct, right? So A here is that someone who sees everyone. And likewise, I can keep the same order of quantification and flip the ordering of the predicate, and that will give me someone is seen by everyone. So there is an X such that any Y I pick, Y sees that X. And who is this someone in the fourth picture? A again, right? You see here that A is seen by everyone. Okay, so this shows us how you can combine these things to get different meanings. Questions about this? Does this help? Okay, it's a very good question, non-trivial matter. Okay, and I also highlighted here. This is going to be important for what we're going to do today. Remember, I'm coloring this X to remind yourself that it refers to this part. Okay, and likewise for all the other ones. Of course, you can do many other things. You can say everyone sees themselves. You can say everyone sees everyone. No one sees everyone. You can do a lot of combinations. These are just combinations you can do with flipping the ordering of the quantifiers and flipping the order of the relation. Okay? Okay, let's talk a little bit about the midterm. So the midterm, how do you prepare for it? You go to the course homepage and you have midterm preparation materials. Okay, I want you to start by looking at previous year's midterms. They have solutions. Okay, if you look, if it works, you will see the general structure of the midterm. Okay, we're not going to change the general structure of the midterm. We're going to keep it like this. Okay, so learn the general structure of the midterm, and then it will help you study what you find like hardest. Okay, so we have some definitions. You have some questions of TFL, some symbolization in TFL, truth table questions, and symbolization in first order logic, and then today's topic as well. Okay? Start by doing the midterms. Learn the structure of the midterm. Okay? Then you have a lot of midterms. Then you also have the entire textbook with all the stuff we haven't done. So to practice the things that are hard. Okay? If you have questions, if you get stuck on something that we haven't covered, this is a good place to ask once we do practice of the midterm. Yeah, you had a question?
Is it possible to get a little bit more information on x is equal to y? Because I missed that. Identification.
Identity, okay. So let's cover it very quickly. So identity, this is like the sign for identity, and it's a special sign. It's not saying that x and y have the same value, like they're not equal in the like simple sense that you learn in maybe in math. They mean x and y are just the same object that are referred to with different names. Okay. Why do we add identity to our language? Because it allows us to express things we cannot do without the identity. So I can say, for example, there are at least two horses. Okay, so I can say there is an X, there is a Y, and then I say X is a horse and Y is a horse. What is the problem here? That first order logic, just like that, doesn't tell us that they're actually different. So from first order logic perspective, we haven't specified that we're actually talking about it. So how do we do that? This is why we have identity. We can also add the information, and by the way, X is distinct from Y. So this says there are at least two horses. Now you can add more and more quantifiers to say there are at least 3, there are at least 4, and so on. So this tool allows you to say there are at least n things.
And why is it at least? And so if you write this down, there are also can be 3 horses.
Correct, yeah.
In this sentence down, there are 3 horses.
If I want to say that there are this says there are at least 2 horses, and it's going to be true. We'll talk about truth more today, but if there are 3 horses, 1, 2, these are 3 horses. And then this says I can pick X and Y to be this one and this one, or I can pick X and Y to be this one and this one. I'm guaranteed that they are different. So the way I'm doing it because I'm lazy is this. Okay, but officially the textbook says you negate an identity by putting a negation in front of it. No, it's okay. Yeah.
What is the scope of negation?
Right, the scope of the negation is only on the identity. If you put a negation in front of an identity, it only fixes the identity. It never will go farther over.
The entire just
it's scope of the entire identity expression. This is why it's a bit confusing, this notation. Questions? Yeah.
When does the negation go further than that?
People, it's hard to hear our students talk at the same time. You can say also something like this, okay? Let's say I'm saying A equals to B, A and B are names, or D is the same as G, okay? This is a sentence of first order logic, right, with the main operator at disjunction. I can negate the entire sentence, right? And then I'm saying either this is false or that is false. So this is why negation is a bit weird, because if you do it immediately in front of the negation of identity, is weird, because if you put it immediately next to the identity, you don't specify the bracket. But if the scope is going to be bigger for the identity, you need to have brackets. Otherwise, you did something wrong in the way you wrote down the expression. Okay. And so it's important, check the slides, check the textbook of how you say there are at least n things, there are at most n things, and then you can combine them to say exactly n things. And this is important for definite descriptions, because when I say the wrestler, I'm presupposing that there is exactly one wrestler. A wrestler exists and there is no more than one. This is a definite description. Okay? We're good? So please go over it, because it's just like a matter of it's just like a few forms, and it doesn't there is no more complication than understanding these forms of at least and at most. Yeah? Yeah.
If we're about to move on, then I have another question. And it's about the condition. Because I read in the textbook that it says if A then B, but it also means A only if B. But how are those two the same? I don't comprehend that it's the same thing. Because when you first one say if it's A, then it's B, and in the second one, A only if B.
Right.
So then it means A.
So the rule that only if is the thing that will show up later, right? Think about the sentence, you're in Tilburg only if you're in the Netherlands. And the sentence, if you're in Tilburg, then you're in the Netherlands. Right? They mean the same thing. If you're in Tilburg, then you're in the Netherlands. And then it has to be that you're in the Netherlands if you're in Tilburg. So in Tilburg, only if you're in the Netherlands. It's not true that you're in the Netherlands only if you're in Tilburg, because you can be in other places in the Netherlands. And it's not true that if you're in the Netherlands, then you're in Tilburg. This is why we kind of emphasize this example, this geographical example, because then you can remember this example and then put these equivalent forms that sometimes it's hard to see that are equivalent into the structure, and it will help you recognize it. Okay? But only, I agree that the expression only is confusing. So I fully on board with that. Whenever when I write down a conditional, I try to first put it into this whenever I start with, I want to make sure that I understand what it means when I say if, then, right? That's the easiest form. So think about ways of taking the complicated form into the easiest form.
Yeah, I do that as well. Yeah, then I found A only if B a little bit more confusing.
Yeah, I agree. So the only if kind of specify what has to be the case if A is true. This is one way. So if you're in Tilburg, it has to be the case that you're in Netherlands, but not the other way around. Another way that the textbook and the slide use this word is it's a necessary thing. But the B is a necessary thing for A to be true. Okay. So this is a good point both for true functional logic and for first order logic. When you prepare for the midterm, make sure you remember how to symbolize in the right order conditionals. Okay? The easiest way to do it is just to remember for this week of the exam that only if has this special way of symbolizing. Okay? Other questions? Questions at the back?
In case 84, A and 4 we discussed the class and over. I still don't see why it won't.
I don't have it. Let me. 1 moment. So 84 of the textbook. These computers are very slow for some reason. So part A or part C? There's a mistake in the textbook I mentioned in the tutorial. Okay, this says, people, let's come back together. It's an important thing to notice. If someone knows the combination of the safe, then it is Ingmar. Okay, so for all x, if that x knows the combination of the safe, then what do we know about that x? That x is actually Ingmar.
Yeah, but is it necessary to add like n Ingmar knows the combination of the safe?
Yes, this is kind of, because this kind of, in English, this is more linguistics than logic, but in English, when you say only Ingmar knows the combination of the safe, you're implying that she actually knows. Okay? And as I mentioned in the textbook, they do it as a biconditional, which is extra confusing. I would advise you to do it as a conjunction, saying, if anyone knows the combination, it is Ingmar, and conjunction, Ingmar knows the combination of the safe. Okay, this guards you against the possibility of empty predicates, no one knowing the combination of the safe. It's a conditional. One way to do it is a conditional, another way to do it is a biconditional. In the textbook solution, you will see a biconditional. Okay? Okay, let's come back. Sorry, I didn't show it, but okay. I think today's class there's a lot of definitions, but it will help you understand first order logic, because note that we haven't said yet when is a sentence true in first order logic. I keep giving you these examples about what the sentence means, but I didn't give you a rule to say this sentence is true, this sentence is false, right? In TFL, we had valuations, specify the true value of the atomic sentences, and then with the valuation, we can figure out what is the true value of a long sentence, right? With truth tables. But we still haven't talked about truth and falsity in first order logic, and this is today's task. It's an intuitive idea, but it involves a lot of definitions. Okay, so if you understand the intuitive idea, that's good, and then try to understand the definitions. Okay. First, there is a distinction in first order logic between sentences and formula. Okay, or formulae, if you like Latin. We need to understand what the difference is. Okay. There are 6 kinds of symbols in FOL. If you combine these symbols, you'll get an expression. Okay, expression is just like a list of symbols. Expression can be nonsense. The same way I can string letters in English, like Michael, hello, Michael. This is not a sentence in English, but it's a string of words in English. Okay, so we also have expressions in first order logic. We want to make sentences out of them. Okay. A formula is going to be any sentence or an expression that can be turned into a sentence by adding a quantifier in the front. Okay, so sentences, this is kind of confusing because we haven't got there yet, but the formula is something that you have, and then once you add a quantifier, it becomes a sentence. So the formula, you can think about it as like the part without the quantifiers for now. A term is any name or variable. So for us, it's very easy. You either have something like A or something like X, a variable or a name, giving you a term. With the notion of a term, we can define the notion of an atomic formula in first order logic. Right? I haven't told you what is an atomic formula in first order logic yet. You know what atoms are in TFL. So what are atoms in first order logic? First, for any predicate and for any terms, depending on the length of the predicate, if you combine a predicate and a term, you get an atomic formula. Okay? So for example, from before, S is a predicate with 2 places, and if I put terms inside, this is going to be an atomic formula. This is also going to be atomic formula. Okay? Yeah?
The 4LX and the...
Okay, so good. So this is what distinguishes the sentences from a formula. The formula is the part, so to speak, without the quantifiers. At the end of the day, we only care about sentences because this is what we can read. So this is why we have this like in-between notion of formula. So you write this is going to be, it's not going to be a sentence just because we have 3 variables. Okay? There's another type of atomic sentences which is using the identity. So any type of this expression, this is also going to be an atomic formula. Yeah.
What is in any place?
Right. So remember that our predicates can have one place, like Michael is a teacher, so we're going to have, this is a one-place predicate, it only takes one term inside. And seeing takes 2 arguments, takes 2 terms, so it's going to be a 2-place predicate. Okay. X is between y and z, that's going to be a 3-place predicate. And then n-place predicate is just kind of like being lazy, I don't want to write for every term, so I'm saying for how many places you have for the predicate, you need that many terms, you combine them, you get a set. Okay, nothing else is an atomic formula. So you either have basically just applying predicates, or you're applying the identity and you get an atomic. So it's a bit like true functional logic, that what is special about atomic sentences, why do they don't have? Quantifier, that's one thing, but what is more like true functional logic? Yeah? You know, they do have predicates, so it's like this, Michael is a teacher, that's an atomic formula, yeah? Right, connectives, people, this is like, we should not forget the connectives. Atomic formula don't have connectives. If you have negations, that's not going to be atomic, and so on. Okay? So here's some FOL atomic formulae. Okay? There's no quantifiers, there are no connectives. It's just like applying the predicates and the identity. Okay? These are going to be our building blocks to build more complicated sentences and formulas. Yeah.
Why do we care? We already use this.
We care exactly because we want to make sure that we know how to build a correct sentence in first order logic.
We already use like all of these examples.
Right.
Now it's a formula.
Right. But then I ask you, it depends for like, in order to give a truth value, you should be able to give truth values to sentences, not to anything else. So you need to know what sentences are, and sentences are built from these atomic parts. The same way in TFL you build from the atomic propositions.
We already made sentences, right?
Yeah, but you didn't know the definition, the distinction between a formula and a sentence.
Yeah, that's right. But to check the thing, we need to check the sentence.
Right. Yeah. So you're right that like this is why I start by saying that like we talked a lot about the meaning of these sentences, but I haven't told you how to kind of like give them truth value. So in order to give them truth value, we have to be very, very clear about the definitions. But you're right that we already thought about all these things. Okay, now we have the recursive definition of what is a formula in first order logic. Do you remember that from true functional logic? Something similar like this. It's a big list. Okay. Every atomic formula is a formula. That's easy. And then you have the connectives, right? If you have something which is a formula, you can put a negation in front of it, and it will be also a formula. If A and B's are formulas, then you can combine them with conjunction, disjunction, conditional, or biconditional to get more formula. Remember here we get the rules for the brackets. Once you apply one of these connectives, you add a bracket. Okay, that's important. Yeah. For atomic formula, there are no connectives. So look at the first clause. First clause says atomic formulas are formulas, and then how do we get the connectives? We combine atomic formulas and more complicated sentences with the atomic formula. Yeah, of course, but not the atomic formula. The atomic formulas are what specifies them that they don't have. Right. Again, the idea is what are the building blocks? People, let's be quiet for a moment. The building blocks for first order logic are atomic formula. You always build anything you have, you build from the basic building block, which is the atomic formula. And this is why we specify, basically in one we say the basic building block is atomic formula. Then you can add connectives to get more complicated formula which are not atomic anymore. This is very similar to. It doesn't mean much. It just means that the building block are atomic formula. Okay. So I will ask you, why is this a sentence of first order logic? This is an expression. I wrote down a list of symbols, right? Why is this not a good expression? Why is it not a formula? It's not an easy way. There's no easy way to answer it. The only way to answer it is to say, look at this expression. I cannot build it from the above rules. Okay, this tells you how you can build sentences. Now compare this to this sentence. This is a formula of first order logic. Why? Because I combined two atomic formula of first order logic, Fa and Gb. And what rule did I apply here? What is the number of the rule? The third rule. Okay. But the third rule says the thing you combine have to be formula, right? So how do I know this is a formula? Rule 1 tells me this is a formula because it's an atomic formula.
Yeah, but then without the NGB, it will be also the normal formula because it says right there in sentence 1 that it's an atomic formula, it's a formula.
Because then it's Fa in a conjunction and without number, so then it's not an atomic formula.
Okay, so leave the conjunction out and just put in just Fa, there will be a formula.
Yeah.
Right, but again, look at this thing. I'm saying I combine this with a rule that takes conjunction here and an atomic formula here. What's wrong with that? You cannot combine it because this thing is not an atomic formula. This is an expression of first order logic, but it's not an atomic formula. You're only allowed to combine atomic formulas to build something. This is the easy part because this is the same as true functional logic up to now, right? Also in true functional logic, you only combine atomics. You combine the connective with atomic propositions, okay? But we also have quantifiers, and the quantifiers are the hard part in terms of definition. Say, if A is some formula, X is a variable, A contains at least one occurrence of X, so this variable is in A, and A contains neither a universal quantifier or an existential quantifier, then I can put a universal quantifier with X in front of my formula. Okay? Example. This is a formula. This is an atomic formula. It has X inside, but it has no other quantifiers. So rule 7 tells me you're allowed to put a universal quantifier in front of it, and this will give you a new formula. Likewise, rule 8 says the same thing for the existential. If I have this kind of thing, it's a formula, it has a free X, the X is not connected to any other existing quantifier, then I'm allowed to put existential in front of it to get a new sentence. Okay? Basically, what 7 and 8 tell you is that if you have a formula with a dangling X or Y, you can capture them with a quantifier and then have a formula. You have a question?
Yeah, because the formula said that any expression that can be turned into a sentence by adding a quantifier but now we've added quantifiers and we still have formula.
Right, so sentences are a type of formula. Okay, this is the way to think about it. Questions on the side there? Questions? It might, yeah, like if any of you are confused, then it's likely that all of you are confused. Okay? You see how I'm using first order logic? So if you have a question, likely that other people have it. Yeah.
So somebody says, somebody asks you, like, is fx the formula? And you say it is.
It is, yeah. Why it is a formula? Fx by itself is an atomic formula because you apply the term and the predicate.
Oh, yeah.
But it's not going to be a sentence because x here is then going to
We
be,
only care about something.
and we only care about sentences. We like to make sure we always have sentences. Yeah.
Yeah, but what is an atomic formula that isn't a formula?
No, there is no thing. Like atomic formula is a type of formula. There are formulas which are not atomic formulas, but every atomic formula is a formula. Okay, this is what I just said involves understanding the conditional. Okay.
Yeah.
If A then B, if something is an atomic formula, this is a formula, but it's not true that if B then A. If something is a formula, then it is atomic formula. Yeah.
If I talk to my parents about this, yes, they always ask, what will we use? Where can we use this? I don't know, where are we going to use this in the future?
Okay. You used it in the past. You see this thing? This thing is impossible to have without first order logic.
It's all complicated.
All of computer science is built on these rules. If you ever tried to write, I don't know if like, just like this, like I'm talking about applications outside of philosophy. If you ever tried writing code, you note that the rules are extremely tight for how to write it. You have no leeway of making mistakes. If you make a mistake with one bracket, the code just doesn't work anymore. The same way, so basically because code is a lot of logic instructions that are based on very, very, very clear rules of what counts as code, what counts as a logic instruction. And this is why we're so careful about like what is exactly the right sentence. For philosophy, you will see next blog how a sentence like this is very important in metaphysics. There exists an A. And you will see with Nathan, there's an entire very famous paper that says that this type of understanding of existence in first order logic is very important to understanding existence in metaphysics as well. Okay, and you only can get that if you understand first order logic. Okay. Okay. Yeah.
It also helps with making arguments, right? Because you have to need to know the proof.
Yeah, so you want to be able to make your argument as clear as possible. And if where do ambiguities come from? Basically by applying language in ways that can be read in two different or more than one way. When you're very, very, very clear about the rules, you cannot have ambiguities. You cannot have ambiguities. Your arguments are very, very sharp and clear. Otherwise, like this entire building, the thing we're building will like crumble to the ground if it's not like has like very clear foundations.
Use all of the rules.
It's used in the background of many things. It's all over. In my perspective, it's all over us. Yeah. There's a lot of history behind these things. Okay, people, let's come back. These are some examples of FOL formulas, and these are not FOL formulas. Can someone tell me why this is not an FOL formula? Sorry?
3 times x.
That's not a problem. This is a between, it can be a three-place predicate.
Oh, brackets.
No. Why is this not a formula? What rule do we bring?
There are 3 variables.
Here.
Yeah. No, 3, as in not.
Okay, that means it's just a formula, it's not a sentence. A sentence is going to be a formula without 3 variables. There's another different problem. Correct. Look here. this x is bounded by two different quantifiers. This should be impossible according to Rule 7. Rule 7 says that you can add the universal quantifier if and only if A has a free x. But here, or like applying the existential, right? You apply the existential here on something that already has x bounded to a quantifier. That's a big no-no. You can only apply a quantifier on an x which is not connected already to any other quantifier.
Rule 8, the same rules with 7, but just an extension.
Yes, that's Rule 8. Yeah. Likewise, here you violate Rule 7 for the universal because if you look at this sentence here, it already has an x which is bounded by a quantifier. Big no-no according to us. Yeah.
The second part of the condition on these x's are free.
Yeah, these are free x's, and that's okay. The same way that this thing is a formula. It's our sentence. Okay? So like in true functional logic, the main logical operator formula is the operator that it was introduced last with our list of rules. And the scope of a logical operator in a formula is the subformula for which that operator is the main logical operator. These are the same definitions in true functional logic, but now we can also apply them to quantifiers. Okay? Okay, as we said, Bxxx is a formula, but it's not a sentence. Why it's not a sentence? Because it has this free roaming variables. We can make it into a sentence by adding a quantifier, and we say we bound or we bind the variable with a quantifier. So now I'm saying there is an x such that x is between x and x, which is a weird sentence, but it's a sentence. X is bound. Likewise, for all x, I bound all the x's here. Okay? Quantifier tells how we can use the variable. Basically, what names can we substitute in the place of the x? Okay? For all says all names. And exist says there is at least one name you can substitute to get a true sentence. Okay? Okay, so a bound variable is an occurrence of a variable x that is within the scope of either a universal quantifier, an existential quantifier, and the variable specifying the quantifier actually match, right? So if it's for all y and you have an x, they don't match. Free variable is a variable that is not bound. Okay? This is something that was in your homework, so I want to make sure you understand this. If I have this sentence, y is free, right? Because there is no quantifier that is connected to y. X is bound to this quantifier. Okay, now we have a harder one. Where is the free variable? This? Okay, you're saying there are no ones. That's wrong. This x, what is it connected to? No, because this x only goes here. Okay? Free variables are variables that are not connected to any scope. How do you, I actually didn't do it in the tutorial, but I can do it in the next tutorial. You can always draw the scope to make sure things make sense. Okay, so the scope of this y is actually all the way here. So any y that falls under the scope is going to be connected to the existential. Okay. Basically, whenever you see x and y's, you want to make sure that you're dealing with a sentence. So it means you want to make sure that they are bounded by some quantifier somewhere. Okay? Yeah.
Which is the free part.
So look, this I'll go over every one of them. This x is bounded by this quantifier. This y is bounded by this quantifier. This x is bounded by this quantifier. This x is bounded by this quantifier. but here I get to an x which is not bounded by any quantifier. Okay. So this is a free x, this is a bound y because it's connected to the first we got. Okay. This is why being careful about the brackets and the way we build sentences is so important, because this can easily make us very confused. Okay? Okay, we care about sentences, formula without free variables, because we said we cannot know how to read formula with free variables. Okay. We have a lot to cover. Yeah.
Can you go back again to that
Yeah.
Yeah. So it was the LXYX.
Right.
Yeah.
Okay. FOL sentences are split into predicates, terms, and quantifiers, right? And an identity. This is all it is. We want to consider what is true for some particular object, right? This is how we use these things to say some things about particular objects. And when we have atomic sentences, and when we add quantifiers, we can say something about all the object or some of the objects. What is an interpretation? Basically, when we interpret an FOL sentences, we are considering what the predicates are true of. We're basically saying the predicate teacher is true of these people, the predicate student is true of that people. We specify it in a very clear way. So let's say we have S is a student as a predicate. The collection of objects that satisfy the predicate, all of you, are what is called the predicate's extension. Okay, so if I have a predicate students in this class, all of you are going to be in the extension of that predicate. I can write down a list of all your names, and that will be the extension of the predicate. Okay, in FOL, we only care about extensions at the end of the day. Whenever we have a predicate, it's basically a group of objects that for this predicate the objects are true. Okay. The teacher in this class, this one predicate, students in this class, another predicate. One of them applies only to me, the other one applies only to you, right? That's the extension. Okay. Nathan, our co-teacher, has a very nice dog. So you can have a predicate D for the predicate, something is a dog that lives with Nathan. We can stipulate the interpretation of the predicate in two ways, either indirectly or directly. Indirectly just means that we give a description of what D is true of. This is how we did things all the time up to now. We just gave indirect interpretations of our predicates. We just gave a description of the predicate. A direct stipulation is, instead of giving some English description of the predicate, I'm just going to list down all the things for which that predicate is true. So Nathan has one dog living with him named Mira. So a direct stipulation of D is just going to be the list with only the object Mira. Okay? Now, why is this important? In first order logic, we can choose whatever we can choose. We don't have to follow English properties or English descriptions. We can pick predicates to apply arbitrarily to any object we want. Okay? We don't care about what naturally goes together in English or in Dutch. All objects have equal footing. So the language is egalitarian. Here's an example. I have predicate Z, and now I'm not going to tell you what the description of Z is. I'm just going to tell you who falls under the extension of Z: Michael, the Eiffel Tower, and everyone who has ever lived in Tilburg. Right? I just created a group of objects involving some metal pieces and some organisms, but this is Z. Well, I've just stipulated directly what is the extension of Z. Okay, now let's say I have the names M and D for Darth Vader, and I can interpret sentences. ZM is true because I stipulated that Michael is in the predicate extension Z. Okay. we don't have any English equivalent to Z. Try hard to think about what is common to me, to the Eiffel Tower, and to everyone who has ever lived in Tilburg, and nothing else. Okay, English won't give you a good adjective for that. Okay, ZD is false because I didn't stipulate that Darth Vader is part of the extension of Z. ZX, we have an issue here. X is a free variable, so it's not going to be true or false. We have no way to interpret it. We can only interpret sentences. We cannot interpret formula with free variables. Okay? Basically, if we have one-place predicates, they are true if the object that's denoted by the term in the one-place predicate has the property or is in the extension of the predicate. Okay, so ZM is true because M refers to the name Michael. Michael is part of the extension of the predicate Z because this is how I stipulated it. So we're done. The sentence ZM is true. Z is exactly this weird group of things. Okay, yeah.
Are extensions like domains, so we have to write down what's in the extension, or just the word to describe?
You should write it down to be as clear as possible, if it's possible. If like all the people of Tilburg, that's too much. But you have to write down the domain, and you have to write down the extension. Yeah.
So the extensions were like A or I or those were the extensions.
The extension is like you specify the group of objects.
Like in a homework with like these two names, Otto and Ingmar.
Yeah, you can.
And the I word extension was the predicate.
Right, you can say who is the spy. You say spy, and then you list Ingmar and Hopper, and then you will specify the extension. Let's take a 10-minute break and come back at 44. Okay, let's come back, people. We have a lot to cover, so I have to continue. Okay, we just specified how a one-place predicate description can be true. Okay, how sentence like ZM is true, but Z here is a one-place predicate. Things get more complicated when we have two-place predicates. Okay, two-place predicate F. First position is friend with second position. Okay. Again, you can have indirect stipulation the way we did up to now, which is basically describing what it means. Fxy is to be true if x and y, if true of x and y, if x is friend with y. Okay, I just describe what it means, but again, I don't have to do that in first order logic, and you can just give a list of all the people who are friends with each other. Okay. So this will be called the direct stipulation, or the extension of this two-place predicate. I'm going to specify which ordered pairs of the objects specify the predicate. Okay, now the order is important, right? Because again, the order of the predicate is also important. So the way you write down a direct stipulation of a binary relationship is with these like ordered pair. Nathan, Michael, Amanda, Michael, right? So I specified that Nathan is a friend of Michael and Amanda is a friend of Michael. I haven't specified that Michael is a friend of Nathan. Okay, but it's true. Yeah, we are friends. Okay. With this direct stipulation, F and M is going to be true. Why? Because I'm saying N refers to Nathan and M refers to Michael. So I have this ordered pair in my extension, so to speak. But FMN is going to be false in this stipulation, right? Because I haven't stipulated that Michael is friend with Nathan. The order matters also when you specify, when you give a direct stipulation. It's very much so. Okay, yeah.
Do you have to do that with those specific brackets too?
If you don't have to. We don't go into these type of notation, but it's kind of like it's going to help you. Just remember, put commas and make sure the ordering makes sense. Yeah. Because think about, like, let's say I have a two-place predicate with two places, and then I write down this is true of Michael, and this is true of Nathan. But this doesn't make sense because
No, but why would you just say like M is Michael, N is Nathan, so F and M means Nathan is friends with Michael. Why not just do that?
with N and M's, that's
Why would we use these brackets and write down the name?
because the brackets specify the order. We don't have the pair Michael is friend with Nathan. We only have the pair Nathan is friend with Michael.
So we didn't have to write these things down right there. Different.
No, you build interpretations now. You make formula sentences true. You have to be able to build the interpretation.
But if I would say F and M, then that's not right.
Yeah, and you just stipulated that Nathan is friend with Michael, but you haven't stipulated anything else. So under this stipulation, we're going to say that this sentence is false. Okay, we want to be able to say the difference between, like, this be true and this be false. So we need a stipulation that is sensitive to the order. Okay? Yeah.
Are the special brackets significant?
They are like they in general in philosophy and logic and mathematics they specify ordering. It's not the end of the world if you don't do it, but you can remember them. Whenever you use them, you specify ordering, and the ordering is important. Okay, we also have identity, but we don't have to stipulate what identity means because it always means the same thing. Unlike capital letter F and G. The interpretation of identity is fixed, and X is Y is going to be true, basically, if they just refer to the same thing. If I have two names, that refers to the same object. Remember, I can stipulate that N refers to Michael and M refers to Michael. And then I'll have an interpretation where N and M are identical. Okay? You cannot decide that the extension of identity is something else. That's not allowed. You can decide the extension of any other predicate, but not of identity. Okay, now we have all we need to say what is interpretation. The way you can think about it for now is that interpretation is, we already talked about symbolization key. Interpretation is like a full symbolization key for first order logic. It specifies everything we need. So what does it specify? First, we specify what the domain is. What is this bucket that we're working with? The bucket of objects. Then we're going to have an assignment of exactly one object within the domain for each name that we care to consider. So if I have the name small letter M, I have to specify that this refers to Michael. And Michael is therefore in the domain. And for each predicate, we have to consider the specification of that predicate. And basically, what the predicate is true of. So we give this full-on specification. Okay? Interpretations, once we have interpretation, everything is fixed. The kind of like the extension of each predicate is fixed. And with an interpretation, we can give evaluation, we can give truth value for every sentence in first order logic. Yeah.
What do you mean fixed?
In here,
Yeah. This was fixed.
you cannot mess around anymore. Once you write this, let's say you specify who's friend with who in the interpretation, you cannot later decide. It's kind of like you working with that. That's who are the friends. If you want to change like who's friend with who, you have to change the interpretation. Yeah.
I don't get the third one. The third.
A specification of what things in what order the predicate has to be true of. So let's an example I think will help here. So here's a full-on interpretation. We have domain, universal, meaning we consider everything. That's okay. We specify the predicate D to be D is a dog. Okay, so we basically say everything which is a dog is going to fall under this predicate. F is friendly. Z, I'm going to specify with an extension. I'm going to say that Z applies to these objects, and predicate A applies to these two objects. Okay? And I only give three names. Is there a name here which has no, is there an object that has no name in this interpretation? Correct. Is there an object with two names? No, so that you're describing the extension of a predicate. Is there an object that has two names on it? Right, so each one of them, this is a different object. So there is no name that has the same object. Okay?
So,
No. Okay. But there are objects with no names here. The Eiffel Tower has no name. That's very important. So this is a full interpretation. Now, any sentence you give me with these predicates, I will be able to tell you whether it's true or false. Okay?
but how would you write down the Eiffel Tower then? How would you fill it in?
We will get to that. If you have relationships, I already showed you an example, you can give an interpretation with a diagram. It's sometimes easier than write down all the ordered pairs, who sees who, for example. So R is going to be a two-place predicate, and I want to write an interpretation, I can just give this picture saying that the object referred to by the name B is related to the object referred to by the name C, and so on for all the other relationships. Okay, so this is a way to, like, if you will, graph like a friend group, right? You can also, it's okay to have an arrow that goes to itself to specify that something applies to itself, so to speak. Okay, so RAD, RDA, and RBC are all going to be true under this interpretation. These are atomic sentences, and they're going to be true in this interpretation. But RAB is going to be false in this interpretation. Why? Okay, I'm looking RAB. Is A related to B? No, there's no arrow, therefore it's going to be false. Okay? So basically the arrows represent the relationship. So the arrow is a very abstract way to represent things like friendship, love triangles, who is taller than who, whatever you want. Okay. When you have interpretation, we can give a truth value for any sentence. How do we do that? Not that easy. Just in terms of definitions. We have three kinds of sentences in FOL. Atomic sentences, sentences whose main operator are the connectives, and sentences whose main operator are the quantifiers. Right? So we want to be able to give truth value to each one of these, or each type of these sentences. Okay? Atomic sentences are easy. This is a long definition that captures a very, very intuitive idea. Okay? When R is an n-place predicate and A1 to AN are names, this sentence R A1 to AN is true in interpretation if R is true of the objects named by A1 to AN in that order. Okay, so this is a very long way to say, here, for example, RDA is an atomic sentence, right? Just apply names to a predicate. And this is going to be true in this interpretation. Why? Because we specified that D is related to A. Okay? Yeah.
Do we specify this, or is this like some drawing?
You can use drawings. Drawings are helpful when you deal with like relationships. Yeah.
Or is it what you make these things, or are they?
No, you make them. You need to make them. We'll see why in a moment. Why sometimes you need to make them for logic. Basically, to show validity. Yeah.
Were those atomic formulas?
Sorry.
You said those are atomic sentences, but were those atomic formulas?
So everything which is a formula, everything which is a sentence is also a formula. Okay. Sentence is a special type of formula. Think about it. And these are sentences. They are formula as well, but they're also sentences. Can someone tell me why these are sentences?
Because they don't have any free.
Exactly. They don't have any free roaming variables. So we know that there are actually sentences. Formula, after all I told you, what you need to remember basically is that the formula, which is not a sentence, is something with a free roaming variable. And we don't like that because we cannot give it interpretation, therefore we cannot give it a truth value. Okay? Why do we build these things, right? Basically want to show, and we will get to that, it's very important. Okay? So we understand how we give a truth value to atomic sentences in FOL once we specify it. Likewise, we have sentences like A equals to B. This is going to be true if the name A refers to the same object as the name B. Okay? Atomic sentences are the easy part. But I'm trying to remember when I first learned it, it's kind of weird that you have the language, like you have RAD, and then you have a picture that says RAD, and it's kind of like the same. So what's the deal of like distinguishing between the two? It's important when we think about quantifiers. Okay? Before, we have it here. Let's look at interpreting atomic senses. Let's do this exercise for a moment. So here we have a fully specified. We have two interpretations. We have the one here. Okay, so we can say RAB is true, RAB is false, right? There is no arrow here. So we're going to say that the sentence in first order logic is false. And here's a different interpretation. I specified the extension of the predicate Z, and I gave two names. So we have a unary predicate Z here. Zn is true. Why? Because the name N refers to Nathan, and Nathan is part of the extension of Z. Likewise, ZD is false because the name D refers to Darth Vader, but Darth Vader does not fall under the extension of Z.
I didn't really get what it's saying then, because if you have set N, it says Nathan. What? Or am I wrong?
No, you're right. It's like this is like where first order logic becomes. It's not always obvious how to translate it back to English. Okay, because now, this says like the name Nathan, and like this property Z applies to Nathan. Okay.
Yeah.
So if you did the homework and you get all right, in the case that's true, I think so, but this would all things you just taught us would be all very natural, right?
These things,
Yeah.
they very much build on the things we already done because we had to translate senses from English and we had to kind of understand what these things mean. But interpretation gives you like a full, clear understanding of what everything means. Yeah. This is why it's always a bit hard to teach you before I tell you what is true or false. Here I'm giving you the definition of what is true or false. But when I give you this example of someone is a vegetarian and I'm saying in this situation it's false, but I didn't have yet the definitions of truth and false. So now we have that and we can speak of truth and falsity in first order logic. Okay, now we covered atomic senses. We need to cover situations where the main operator is a connector. This is where you use your true functional logic brain and you remind yourself the truth table, the true functional logic, to remind yourself how things work. So we're actually not using truth tables here. We're kind of capturing the idea behind every truth table with a sentence. So if I have a first order language sentence with the main connective negation, this is going to be true in interpretation if and only if A is going to be false in the interpretation and vice versa, right? That's what the truth table of negation captures. A or B is going to be true in interpretation if either A is true in the interpretation or B is true in the interpretation, right?
It kind of is a truth table, right?
Right. Yeah. It's kind of like a way. It's a way to compress the truth table in one sentence. Yeah. The tricky one, maybe like I hope it's easy now with the truth. When you learn the truth table, if A then B is true in interpretation, if either A is false or B is true in that interpretation. So remember the truth table for the conditional said this is true in every line in which either A is false or B is true. Okay. But remember, you cannot use truth tables to kind of figure out the truth value of any first order language FOL sentence because we don't have the truth values for quantifiers. Okay, so it only helps you in the case of connecting. Okay, questions? Okay. Biconditional AB is true in a particular interpretation if A has the same truth value as B in the interpretation. Either both of them are true or both of them are false. Okay. So same idea in true functional logic for the connectives. Let's look at an example. So in the domain now is all the Simpsons characters, all the objects in the Simpsons, and we have predicates specified indirectly. A is an American, B is a baby, O1 is older than O2, and I have two names, Maggie Simpson and Homer. Did I specify all the names for all the objects? No, right? I only have two names with many other characters. Give me another character. Bart. Good, yeah. So We still want to talk about Bart, although we don't have a name for Bart.
Would that be an accent or the variable?
Right, we'll use access to kind of like get to Bart, basically. But first, let's think about connected. Is it true that not OMH? Is it true or false? It's true, right? Maggie is not older than Homer. Is this true?
Yes.
Yes. And is this true?
Yes.
So is the conjunction true? Right, yeah, because each conjunct is true.
Is Maggie big?
Maggie's a baby.
March.
Is this true, this sentence?
Where?
Yeah, the entirety of the sentence. Yeah.
Yeah, that's because it's all.
Or, okay, this is important. A disjunction is true if either disjunct is true. But look at this funny sentence. H is equal to H. Can this be false? No. This is always going to be true. So this disjunction is always true.
Well, except if Maggie wasn't a
No, it doesn't. I don't even care about the other disjunct. I know that this disjunct is always true, and the disjunction is true if at least one of the disjunct is true.
Oh, yeah.
Right. So here's a kind of like a shortcut, if you will. Is this sentence true?
Oh, the sentence is true, yeah, but.
Oh, so it is valid.
The conditional. It's a conditional, right? So the antecedent is false. Because Homer, the name H and the name M refer to different objects in my interpretation. So the entire sentence is true. But sometimes H and M might refer to the same object. So just here in this interpretation, they don't. Yeah.
So we don't really stipulate the values, right? We know because we know the character.
Right, you don't give a direct stipulation, but you could, right? There are only finitely many. There's a poster with all the characters,
Yeah.
and then you can like write a list of all the possible phrases. Yeah, in the back.
You said the first disjunct is true, so the whole disjunction is true.
Correct.
But if you look at what they mean, so Homer is Homer, or Maggie is not an American, but if she would be American, we know that both are true.
Right, and it's an inclusive one.
So how is then this still true?
Because this is false. Maggie is an American.
Yeah, but just in case if the negation was gone. So now you could say
Okay, Maggie is an American,
Yeah.
and Homer is Homer. So both of these things are true.
Yeah.
And the disjunction is true if at least one of them is true. At least one. You remember at least one? I talked about at least one.
Or implies that it's either one. Right?
Yeah. So it's still the inclusive order. It's enough for one of them to be true, one of the disjuncts, maybe two of them are true, in order for the entire disjunct to be true.
The last one, the sentence were switched. So the first one, the last one, the negation was first. Then it would be false. Conditional, right?
And so this is a false sentence because Homer is an American. Maggie is not identical to Homer.
Yeah.
So this is false, basically. This is true. So this entire thing is false. Okay, this is how I write it down. Like this is how you should start.
It's negated, doesn't mean that it will be true again.
Right.
If you read these atomic sentences as the same as TFL, it's
Right. So what are we doing here? Are we just doing TFL? No. In a moment we'll use quantifiers and then
that's gonna be fucked up.
your language. People, you have questions?
Yeah, but they don't find out.
People, you have questions? Questions? Okay, another question?
In case that H and M and Q specify the same name, how would you write it down in the red?
You would just write down,
M is Maggie and H.
you can write maybe, you could just say H refers to Homer.
This never happens, right? Because,
Of course it does.
but like, why would you say M is Maggie and H is Maggie?
Because with Samuel Clark.
What?
With Samuel Clark.
how do we?
Oh, okay, you could be, okay, like
Who is
you.
this woman?
Oh, okay.
Sometimes, many times, the same thing has different.
Okay, but it would be literally like the name again, it would be dumb.
But it's
It happens in life that the same object has two names. Actually, we'll learn about, I don't know if you've learned about Frege, but there's like a huge story behind this in philosophy, but not for this. Frege. But sometimes, objects have the same name. There's not, the same object has different names. Samuel Clarke is the author Mark Twain, so he goes by two names. Kierkegaard, the philosopher, had 70 other names he used as like his pseudonym. Okay. Okay, let's think about quantified sentences. Before we go into the definitions, I want you to make sure you understand the idea. If I tell you there is someone who is older than Homer, is this true in my interpretation? Right? Why no? No, I only specify the name Maggie and Homer, but I also specify the domain involves all these things. So there is someone who I haven't named, and it's Mr. Burns. Okay, let's say. So it's true. This first sentence is true.
But it could be true, right?
No, it's again. This is why we fix an interpretation. No, could we? We have a fixed interpretation, and according to that interpretation, we ask whether it's true. Okay. So given this interpretation that involves all the sentence characters,
Then I must have the info.
right? Yeah, it's not fair. This is why it's better to write down
I
the
do in this case, but.
right. Yeah. So we will see when you build up interpretation, there are ways of like you can basically have like only 3 objects in the domain. You don't have to have such a big domain. You can have very, very small objects. Small domain.
So the domain could have been Maggie Simpson and Homer.
Right, but no, you change the interpretation. This is why I always say yeah, but then it's a different interpretation. Given this interpretation, this is true. And what we know about the extension of O, right? Okay. By the way, you can list all the characters of Simpsons and write down for each 2 of them who is older than who. So you can write down a full extension of the predicate. There is someone who is older than Maggie and is not American. This is like really requires some Simpsons knowledge.
Are there only American? It is true.
Who is it?
Also,
Willie the gardener.
Yeah, groundskeeper Willie. Okay, so there is a character in Simpsons. There is a character in Simpsons which is older than Maggie and is not American. Okay, so it is true. Let's look at the last one. Yeah. Okay. Let's go over each one of them. Now, how we do it in kind of like the official way. We can always extend our interpretation by adding new names that refer to some existing object in the domain. Okay, because Mr. Burns is also already in the Simpsons character, we can basically extend the domain with the name for Mr. Burns. And now the sentence OBH is true, right? Burns is older than Homer. So this is how basically we make existential sentences true. We find 2 names in the domain that it makes it true, and if we don't find it, we can always extend, given a fixed domain, a name for some characters, so some object that we don't have a name. Okay? Again, same situation here. We can add a new name for an existing object in the domain, G for groundskeeper Willie, and then we replace X with the name G. We get this sentence, and this has no quantifiers. We know how to give a truth value for that, right? Okay. What about universal sentences? we have to be able to extend for any, we have to give a name for any possible object in the domain. Okay? So basically, we have a new name for any object that we have in the domain, no matter if we named it or not already. And then you notice whoever A names, this sentence is going to be true. Okay, because this is a tautology in true functional logic. So this first order language sentence is true. Okay?
Okay, but so we just specify no one.
No, you say like I have a name that will refer to any arbitrary object. This is the way to think about it. And then you replace.
Down like A and then without.
So it depends. Yeah, you can say A refers to like if you want to show that this quantified sense is true, you can do that. Yeah, but most of the time you want to show it's false. So let's look at an example here. For all x, there is a z such that z is older than x. So what does this mean? Yeah, but there is an oldest character. So it means that for every person any character you pick, there will be another character which is older than them. But this is not true in our domain because we have finitely many characters and one of them is going to be the oldest. Okay? So here we take A to be the oldest character. A names the oldest character. We won't be able to find anyone in the domain with a new name B for the existential Z that make OBA true. No matter who B names, OBA is false in the extended interpretation. So it's impossible to make this sentence true, therefore this sentence is false. Okay? Now, how do we give an exact definition for this? Let's say we have A as a formula containing at least one instance of variable x, and that x is free in A, and C is a name. We call C here the instantiating name of the variable, right? So what we do is we basically replace every instance of the variable x with the name C, so we instantiated the variable. And we call this formula the substitution instance of these things. So if there exists an x which is either fx or for all z, lxz, I can instantiate the existential x by replacing it with the name A, and I get this sentence. Likewise here, I'm replacing the x with a j. Okay, so this is the idea of instantiating name. And with this idea, we can give the definition of truth of a quantifier sentence in an interpretation. So it goes like this. For all x, some formula A with x inside it is true in interpretation, if and only if the sentence where you replace x with a name C is true in every interpretation that extends the original interpretation by assigning an object to any name C. Basically, again, the idea is kind of intuitive. For all x, AX is true if you can pick any name, even for objects that don't have a name. And then once you replace the x with this new name, you'll get a true sentence. There exists x, AX is true in interpretation if when you replace the x with some name, it's going to be true for some interpretation that extends the original interpretation by assigning an object to some name C. The only thing, the interpretation is fixed, the only thing you can add is add names to objects that don't have names. Yeah.
So is this the same as like having a ball and picking one out? That one you pick out is then C?
Yeah, basically you can say I can randomly pick a ball, I'll call this ball C, where C is kind of a name that I haven't used yet. It's a fresh name. And then I say, I'm calling this ball C, and then let's see if the sentence I got is true. Yeah?
You should put this in the truth table.
There is no-
seems to be like truth.
There are no truth tables because there can be infinitely many, for one thing, there could be infinitely many objects in the domain.
So how do you know? Okay, yeah.
How do you know? It becomes harder. This is why truth, first order logic is much harder. You cannot put it into a truth table. There is no way to just put it into a list of all possibilities. The number of possibilities is infinite.
If you have like a logic paper, do they specify which language they use, or do they just use?
Yeah, they're very clear in a logic paper. There's a section called language, and they specify exactly what is a sentence and what is not. So in a way, every logic paper starts with like something, unless it's like common, or like they work on something, like something which is common. Okay. The idea for all x, a, x is true. If a, c is true, no matter what object in domain we name as c, and there exists x is true if there is some way to assign a name c to object c. Okay. People, now we did all this work, and in the last 10 minutes we were actually going to use it. You'll see why we done all this work, because we can capture semantic notions like validity and logical truth and contradiction now for first order logic. Okay? We have defined truth in first order logic. We can use it to make sense of semantic notions that we care about in logic. We care about validity, right? We said that logic is the science of validity, and validity is a semantic notion. Remember, we did something similar in TFL, but we always use truth tables, right? We said a sentence is a tautology if the column of the main operator is all truths. The difference is that we don't have lines of a truth table. First of all, we don't have valuations, we only have interpretation. But there can be many, many, many interpretations. And if in TFL, there are only like a restricted number of valuations you can have. Okay, and we're going to use the double turnstile, this symbol, to represent entailment the same way we did in true functional logic. Okay, so I'm going to throw at you a bunch of definitions of semantic concepts. A1 to An entails C. When is this going to be true? If there is no interpretation in which all the premises are true and the conclusion is false. So now we have a definition of entailment in first order logic. Likewise, we say that C is the conclusion of the premises A1 to NA, or in a valid way, if there is no interpretation in which all the premises are true and the conclusion is false. So it's the same definition of validity that we had, but we now, in order to make it work in first order logic, we use interpretation.
Why do we say nothing about the first sentence?
Sorry?
Why do we not? Why don't we say anything about validity in the first sentence?
Yeah, it's just like it's still in first order logic. Validity is the same thing as this. So in first order logic, these mean the same thing. Why do we have different definitions? Because remember, we had something very similar to functional logic, but the definition of validity in true functional logic didn't mention any interpretations. So we have to be a bit careful. Validity has kind of like it's the top notion, and it has different kind of like specification for the particular logic that you work with. Although they always capture the same thing. It's impossible for all the premises to be true and the conclusion to be false. When is something invalid? If there is some interpretation in which all the premises are true and the conclusion is false. Right? A sentence is a logical truth. We write it down double turnstile L, A, without any premises, if it's true in every interpretation. Okay? No matter what interpretation you give, A is going to be true, no matter how you specify it. There are such sentences. Likewise, A is a contradiction if A is false in every interpretation. Okay? Note why is this interesting? Because we're talking about every interpretation. But I just told you, interpretation, you can like be very, very imaginative in the way you build up interpretations. Yeah.
Would you say that something is rather logical if the domain is small?
If something is a logical truth, it's going to be true in every interpretation, in every size of the domain. It can be.
I know, but isn't that like potentially bigger? The domain is small.
The bigger the domain, the harder it's going to be for it to be true. Right? So the size of the domain doesn't play a role in the notion of a logical. Yeah.
Why do we use logical truth instead of tautology?
Because tautology is just like a term that is specified for logical truths that are true in true functional logic. That's kind of just a notation. Yeah.
So some sentences can be logically true, just domains and nouns and others. So like if my domain is every
No.
person,
If something is a logical truth, it's going to be true in every interpretation you consider, under every domain you consider.
Okay.
What is the only restriction on domain? You probably forgot that. There's one restriction on the domain. In first logic, it has to have at least one element. So you're not allowed to have an empty domain. But apart from that, the domain can have two objects, one object, infinitely many objects, uncountably many infinite objects, blah, 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 blah. So it's going to be very hard to be a logical truth in first order logic because there are so many options for so many interpretations. But think about it for a moment and then you realize there are many logical truths. Yeah, one. Interpretation is basically something that looks like this. You specify the domain, you specify the meaning of all the predicates, and you specify the meaning of the names.
So like this whole red block is.
Yeah, whatever red block you give, the sentence is going to be true. Okay, so let's look at some example. Okay, consistency and joint consistency. Sentences are consistent if there is an interpretation where they're all true. Inconsistent if there is no interpretation that makes them all true. Okay. Okay. Now we combine the ideas. To show that A is not a logical truth, it's enough to write down one interpretation in which it is false, right? Because logical truth says it's true in every interpretation. To show that A is not a contradiction, it's enough to show one interpretation in which it is true. So this is exactly why we need to know how to build interpretation. I might ask you, is this a logical truth? And you will tell me, no, here's an interpretation in which it is false. Okay? Basically, we build the interpretation given what we're after. We specify domain, give names, stipulate extension. Let me give a few examples because we're very short on time. We have the sentence, there is an x, fx, then a, b. This sentence, we don't know anything about f or a and b. We don't know anything about them. We want to show it's not a logical truth. So we need to come up with an interpretation in which it is false. Okay? Basically, we're looking for a situation where the antecedent is true and the consequence is false. So how would I do that? First of all, I'll give two names for different objects. A and B refer to different things. And fx being x the fox. Okay. Why is this false? Let's see if... Yeah. So here, the interpretation... yeah.
It's not a those.
Sorry. F is this is the interpretation because it is F if it applies to everything which is a fox. So there is something which is a fox, fantastic Mr. Fox, but A and B are not the same. Okay, so I can instantiate this to get FB. Then if A equals to B, this is false. This is true, so the entire sentence is false. So I showed that the sentence. There's an interpretation in which this sentence is false. Quick, yeah?
Just alone the identity is false as well, so then the whole sentence is false.
Right, but remember, because you're doing something, you have to ask yourself, what is the main logical operator? Here, the main logical operator is the existential quantifier, so you have to start with working with the existential quantifier.
So logical truth depends on the main operator.
Yeah, for sure. It's also not a contradiction, because I can come up with a completely different interpretation in which it is true. Okay, so it's neither a logical nor a contradiction. How do I do that? Now I make sure that the names A and B actually refer to the same object problem. Okay, so we have an interpretation in which it's true. There are no restrictions on the interpretation. This is why first order logic has so many possibilities on it. Yeah.
You cannot make or decide whether it's logical truth or contradiction if you don't know specific things about the domain or the interpretation part. You have to know things about it.
No, you make it up. Remember, this is just a sentence that has, you don't know what F is, you don't know who A and B are. It can, you only, when you specify interpretation, you can say it's a logical truth.
Yeah, but with the Simpson example, I have no clue about Simpson. How do I know if it's true or not?
So it depends what you're after. If you want to give a logic, you want to show something is not a logical proof, you come up with any interpretation. It doesn't have to be about Simpsons. Okay? I want to show you last example, the most important one, for validity. This is something that some of you were confused about. Is this sentence entails this sentence? I'm going to show you that it's not. How? By constructing an interpretation where the premise is true and the conclusion is false. Okay? So let's say the domain is Jake the dog, Robin Hood, and F only applies to Robin, and the name A refers to Jake. On this interpretation, the conclusion is false because the antecedent is true. There is someone who is an F, and Jake is not, doesn't have the specification of being an F, so this entire thing is false. But the premise is true because I can instantiate the existential quantifier with an A, getting the sense if A, then if A, which is true. Okay? So the premise is going to be true in this interpretation. The conclusion is going to be false. So we have an interpretation where the premise, all the premises are true and the conclusion is false. So this is an invalid argument. Basically, whenever you want to show invalidity, you need to find an interpretation in which all the premises are true and the conclusion. So showing invalidity is kind of easy. You only need one interpretation. Okay, we will finish here. This is the most important notion, how to show that an argument is invalid. Okay? I will cover the rest of the exercises or like the ideas here in the start of next class.